Welcome to this session. I want us to look at the new subtopic that we are supposed to take on, that is the need for gas exchange surfaces. Now we know that organisms do respire, that is living organism, and the respiration normally need oxygen as a substrate here. Now, for the oxygen to be taken in, it must be passing through a surface. So there is that taking in of oxygen during respiration, which the organism need, and also there is the release of byproduct, which is also carbon dioxide as one of the byproduct that comes out. So if this is the thing, we therefore realize that there is always a need for the organism to exchange these two gases between themselves and the environment where they live in. Like, for example, the organism must be taking in oxygen from their surrounding, and then they'll be releasing out the carbon dioxide to the same surrounding where they live in. So be it air, be it water, where they live in, they need to exchange these particular materials. These particular materials will always be moving in by simple diffusion, which will always rely on a concentration gradient, which we have studied in the previous chapter. So we can therefore clearly see that we need to have the surface area that will always determine how these particular materials are moved. So I want us to clearly look at them in terms of individual organisms. Like we can talk about gas exchange, the gas exchange in small organism. Now, small organism here, we will be referring to the unicellular organisms and other microorganisms that are very small in size. So if the organisms are small in size, what are the things that are going to determine the movement of particles across them? So going back to the principles of the surface area to volume ratio to guide us here so that we can really see, we will realize that the organisms that are small in size, like the amoeba for example, they are having a bigger surface area that is exposed to the surrounding. So therefore, and the need for these particular gases here is not as much as the one that we see in like big organisms. So they are not that needed very, very urgently, or they are not needed in a very, very large volume. So the surface area that they are exposing to the surrounding is actually wide, like we have seen the surface area to volume ratio. And I want you to remember that there is difference between the surface area and then surface area to volume ratio. Now, if we look at the organism like amoeba, amoeba is a unicellular organism. So looking at it biologically, the surface area that this organism has is actually small. In terms of the size of this organism, it has got a small surface area. That is very true. But if we look at this in the ratio of the volume of this organism, we will realize that that ratio is going to tell us that however much the surface area is small, but in terms of its size, what it is exposing to the surrounding in terms to its size is actually a bigger surface area. And that is now the difference between surface area itself and surface area to volume ratio. So in terms of the surface area to volume ratio, this organism has got high surface area to volume ratio, which means that it is exposing a bigger surface to the surrounding as compared to its size. Therefore, in such organisms, just a simple diffusion is going to be enough for the gases to be moving in and also the waste product to be moving out. And that, remember, is in line with the concentration gradient that we have been talking about. So that is one thing that we should remember here. So small organism will therefore not need a very elaborate system like we will be seeing in large organisms. So we will realize that they are exposing large surface area, and therefore the simple diffusion is just enough to supply the gases that they need and also to eliminate the waste product that they don't need in their body. And therefore they can sustain their life through this process in water where they stay, or even on land where they stay. So that is what is seen in the small organism, gaseous exchange in the smaller organism. So that is the thing that I want you to understand here. So there is no specialized system here for gaseous exchange in this group of organisms. Reason being the surface area that they are exposing to the surrounding is so big in terms in consideration to their volume, and therefore that process is just enough. Now I want us to look at How does it happen in large organisms? So gas exchange in large organism. Now I want to believe that up to this moment you are able to clearly separate the surface area and the surface area to volume ratio and how it works. Now if I take an example of a large organism in the atmosphere, like a horse, for example, or a human being. Now if you look at the human being, in terms of the surface area that we have, we look like we are large in size. So human being are large in size. So this one means that we have got a large surface area. But in terms of exposure to the surrounding, what is the proportion that we are exposing to the surrounding? It is a smaller proportion. Besides, animals like mammals, human being, we have got very many cells. We have got the very many internal cells. We have got the tissues that are organized into organs, and then we also have got cells coming in. All of this needs energy. All of this needs energy. All the cells in our body, all cells need energy. That is one thing that is there. And I've talked about the number of cells that we have. We have got the billions of cells. There are very many of them in our body. Now, these particular cells, I also want you to note that these cells need energy very quickly or rapidly. So the need of this thing is very rapid. That is one thing that is also very much important for us. Now, for this particular energy, or for this particular energy to be produced, we need some materials like oxygen and nutrients. Now, for the nutrients and oxygen to reach this particular very many cells in a good time, it must be quick enough. And since we are exposing a small surface area to the surrounding, that one will therefore means that this group of organisms will need a system which will enable them to make these particular materials to move a little bit quickly than it might have happened through simple diffusion. Like if we look at mammals and birds, these mammals and birds, they need to maintain constant body temperature. So this one means that the rate of respiration in this group of organisms is high. So they have got high metabolic rate. Therefore, there is that particular need to supply these materials quick enough so that they can maintain that. Actually, the maintaining of the constant body temperature in the birds and mammals make them to be active in every situation where they are, so they can maintain that temperature, whether they are in polar region, which is so cold, whether they are in the tropical areas, which is warm enough. This group of organisms will still need to be active, and therefore they really need to maintain that respiration very quickly. So we can see that in this case, the surface area to volume ratio will not help. I mean, the diffusion alone will not help us. Though in exchange of the gases between the blood and the lungs here will depend on the diffusion, but we still need that active transport of materials, not just the passive one of the diffusion here. So this particular group of organisms must have a proper, well-developed or specialized transport system, like the circulatory system that we do have in mammals here. So this is very much important for us to note that in large organisms, we depend on a system which is well organized. Reason is we are having a small surface area exposed to the surrounding. Therefore, diffusion alone may not be enough to help us to supply enough materials that all our cells need. So we need a system to facilitate that so that it can be quick enough. Now, we also, after looking at the need for the surface area and the two different organisms, I want us to look at the properties of the gas exchange system, especially in the large organism. How should the gas exchange system membranes look like? What are the things that they should be having in common so that we see how effective the process can be in the organism? So that is one thing that we should be understanding. So let us look at those key properties of gas exchange surfaces or systems. Now I want to believe that maybe you have met this, so maybe we can be talking about them into details. So the first thing that I want us to look at is the surface area. Now what should we say about this? This is a thing that we should be understanding, and it is good to note that the moment you have got a big surface area, that one means that you are going to have efficient movement of the gases, and the volume of the gas that is going to move across that membrane will be large enough. And the moment you have got large volume here, the metabolic processes that we are going to talk about here, that we are going to use here, are going to be quick enough. So we say that the bigger the surface area, is worth noting that the bigger the surface area, the moment that the surface area is actually big enough, that one means that more particles will diffuse across. More particles will diffuse across, and in this case we are referring to gases like oxygen or whatever materials was moving across that membrane. So that is one thing that is very much important. So you'll be seeing how big the surface area of gaseous exchange, for example, human beings are, and maybe all other organisms that we are referring to. So that is one thing that is worth noting. Then there is also the concentration gradient of the particle diffusing. The concentration of the particles diffusing. Now, how is this is a factor here? We know that when we are talking about gaseous exchange, we have got two regions that is separated by a membrane. Like if I can draw here, I can have, this is a membrane, this is the particle from A, this is maybe the inner side. Now last time when we were talking about diffusion, we saw how particles normally move. So if any case these are my particles to be moving here, first I will be looking at their numbers here, and then on the other membrane here. Now the moment there is that difference in the number of these particles, there is that particular chance of motion taking place. So they'll be moving in that manner. So if any case I can be having more of this particle here as compared to what you are seeing inside, I am creating a steeper diffusion gradient, and therefore this one will be making it effective for these molecules to move from the outer membrane to the inner membrane here. And that is a very key factor for us to note when we are talking about the movement of particles. So if we can really maintain, like the cells normally maintain this, like we're going to see how our cells can maintain the concentration gradient such that the particles, their numbers keep on balancing. So if any case these molecules come in, like we learned in the last chapter, there must be that mopping here on this surface here. And what is that mopping? That is the taking away of this particle here, either in the organelles that will be using them up for cellular respiration, for example mitochondrion, or these particular molecules here will be converted to new things so that their numbers keep on reducing. So when it is maintained like that, the concentration gradient will remain steeper, and therefore there will be that continuous diffusion of particles as much as we may need them. So that is a key factor. Therefore the concentration gradient here, concentration of particle, is a key factor for us for the diffusion of molecules to take place across the membrane, and the membrane must be assisting in maintaining that. Then the next thing that I want us to look at is the thickness of exchange surface. The thickness of exchange surface. Now what do we mean here? Now this membrane that the molecules are going to pass across, its thickness or its size is going to determine how quickly the molecules will be passing across. I want to illustrate by assuming that we have got a membrane that one, like in A, have that size, and then I can have membrane B here that is a little bit thicker than the other one here. So this is membrane B. Now, if we were to look at the speed, the rate at which the particle can be passing through this membrane, we will realize that they are not going to be the same. The same time that they can take in A is not the same time they can take in B. Why? If the size here, like when we call this, we can call this one thin membrane, or thin surface, and then this is a little bit thicker, so we can use this word thick surface to refer to this one here. Now, if we look at it in terms of the thin membrane and the thick membrane that I have here, in thin membrane, the distance looks short, and in the thick membrane, there is more distance to be covered. So if we have got more distance to be covered here, it means that it will take a little while for the molecule to pass through that membrane. Therefore, it's going to take time. When you look at it in the thin membrane here, the distance I've said is short, and therefore the molecules will be taking a shorter time to pass across, and therefore the rate of the movement of molecule across membrane A is going to be much quicker than it is seen in the membrane B. And that is one thing that will always determine the speed by which the molecules really pass. So these are really important properties that the membranes normally have. So they must possess these properties, and we'll be seeing them into details how much this one is very important. Though we have talked about each one of them, but still we are going to meet them in our discussions to come. So these are the things that we must look at. So if I am talking about a membrane of gaseous exchange, like in the case for a human being, the lungs, we will be seeing how the lungs is going to be adjusted so that it ensures that the surface area is big enough so that we can take large volume of gases. If we are going to talk about the gaseous exchange in the lung still, in terms of the concentration of the particles, we are going to see how our lungs is going to make sure that there is always a steeper diffusion gradient across it, so that there is that continuous flow of the particles, and also the distance here, the thickness of that surface of the lungs. How is it such that it will make sure that the molecules normally move in across as it is required, or as it should happen? Those are the things that we are going to relate. We have got various surface areas for gaseous exchange, like for example, we have got in plants we have got what is called leaves. Leaves really help in the gaseous exchange. We have got mammals. We have got the lungs, is a surface for gaseous exchange. Then fish, we have got gills, helping in the gaseous exchange. Some other animals can also do it through the skin, like the frogs. The frogs can do their gaseous exchange through skin, though not all animals can do this one. This one is very important to note, that this is very special for the frogs. So those are the things that we are going to see when we are talking about the gaseous exchange system. And then we should note that the gaseous exchange here must also have modification to make sure that these particular properties are retained. Now, we will always understand that we can calculate the rate of diffusion of the gases using the law that was invented by Frick. So we have got what's called Frick law of diffusion here. So maybe we can understand this formula of the Frick and know what he's talking about, how it determines the rate of diffusion here across the membrane. So Frick formulated that if we want to know the rate at which the gases are being diffused, so we can say that the rate of diffusion according to Frick's law of diffusion. This is what the Fick, not I call this guy is called the Fick. Now this is what he came up with. He said that if we have got the surface area of the molecules, you multiply by the concentration difference. And then this one you divide by the thickness of the membrane. Thickness of exchange surface. Now this one should be giving us the rate at which the molecule is diffusing. So the rate of diffusion is given by surface area times the concentration difference divided by the thickness of membrane. And this formula is really telling us one thing, that in any case, if we look at anything that is going to increase the surface area, and then anything that increases concentration gradient, and then you lower this value here, the thickness here, the rate will be high. That is one thing that this guy is trying to pinpoint. And therefore, that means that the surface area must be, the organisms themselves must have an adaptation such that they always make sure that this particular surface area is up, that is high. They maintain the concentration which can be high, and then they tend to have a lower thickness here, so that the molecules can be moving quickly. That one will be facilitating the rate of diffusion. So that is the first thing that I want us to note in the introductory part of the need for gaseous exchange system. And therefore, from here we'll be talking about the individual organisms and how we can formulate this. So that is the most important thing that I wanted to note. Thank you very much. Let us meet next.